So in the last class, we discussed this particular thing that whenever there is a loop which is placed in a uniform magnetic field, then that loop will experience a torque like this. Yes or no? Torque will be equal to m cross b, where m vector is nothing but I into n into a vector. Yes or no? And this was also equals to I into n into a cross. This is what we discussed in the last class. Now, please write down the heading. पहले पोटेंशियल एनर्जी के बाद में Can you see, guys? Is this the same thing as your electric dipole placed in an external electric field? Yes. And what was the torque in that case? In that case, the torque acting on that dipole. Suppose if there was a dipole and that dipole was placed like this. Suppose this was minus q charge, this was plus q charge. Basically, this was the direction of P, right? Everyone remembers the
Yes,
electric
sir.
dipole concept, na? So this was the direction of P, and let's say this is placed in an external electric field like this. Then it experienced certain torque, right? That torque was given as P cross E. Yes or no?
Yes,
Similarly,
sir.
if suppose there is a loop over here, and let's say the magnetic moment of this loop is M, and this loop is placed in basically a magnetic field B vector. So can you see, guys, again this is the same thing. Is this and this analogous? Can you understand the analogy, guys? Here the torque was P cross E, here the torque was M cross P. Do you remember, guys? Here the potential energy was minus of P E cos theta. Right?
Yes, sir.
So here the potential energy in this case it will be minus of MP cos. Okay. So we'll learn about this now. Okay. So we'll learn this. Interaction energy of a current is carried. Please remember, this thing is only possible. This thing is only possible. So you write the condition. This is only valid when you have a magnetic dipole. And for that, the loop should be small. Generally, the loop should be small. Okay. Generally, the loop or coil should be very small, guys. Is this clear? So now let's try to find out the energy. Although it doesn't have a derivation in your school, if you want the derivation, so you can do like this. Suppose you have a you have a magnetic field like this. So suppose guys you have a magnetic field like this, and uh, and let's say a loop is there. Can you see this, guys? Can you see this loop? It's a rectangular loop with a magnetic moment vector like this. Is it perpendicular now? Diagram also almost it's not proper. Yes, yes. Now are you able to understand the loop? Now is everybody able to understand this loop, right? Hello, guys.
Yes,
Can you hear
sir.
me? Hello? Hello?
Sir?
Can you hear me? Hello?
Yes, sir.
Yes, sir.
So this is your magnetic moment, and can you see, guys? Initially, what? Yes, yes. Everybody is able to see the initial case, right? Everybody is able to see the initial case where the angle is theta. Okay.
Yes, sir.
Now, basically, what am I doing? I'll rotate this thing by a small angle d theta. So when I rotate this by a small angle d theta, so can you see over here? In this particular case, let's assume that magnetic moment makes an angle theta with the magnetic field. So at that instant, the torque acting on the loop will be, what will be the torque acting on this instant? Torque will be equals to
MB sine theta.
mv sine theta or m cross b if I just want the magnitude. Yes or no? Yes or no, guys? Can you see the torque by the system is acting clockwise? Can you do m cross b? Can you see if your fingers are curling clockwise direction? So basically, torque due to external agent will be anti-clockwise in the same direction. Can you see the work done to rotate work done to rotate the coil by a small angle d theta against the magnetic field will store as the potential energy of the magnetic potential energy. Okay, so can you see when you do this, the work done by external agent and this will be stored as the potential energy will be equals to the external torque multiplied by what? D theta. Yes or no? Everyone knows this thing. Work done is equals to F dot S, and in angular terms the work done is basically tau dot theta. So anyways, we wrote like this. Now see over here guys. Can you see external torque is anti-clockwise. Even you are moving it anti-clockwise, so hence the angle between them is 90 degree. So on also please remember the magnitude of a system torque and the magnitude of torque external should be equal, and this should be equal to mv. So basically when you do this, it will become mv sine theta d theta. Is this clear guys? Hello? Is this clear? This is the potential energy stored. Is this clear?
Yes, sir.
So work done to rotate the loop from theta equals to theta I to theta equals to theta f will be. That is basically what you want. Control C. Control V. So can you see over here guys? Suppose if I want to make it from theta I to, so basically if I want from here, let's say I increase the angle, let's say to here. So can you see guys over here? The loop has traveled a certain angle. There is a difference between theta I and theta f. So this is the initial case and this is the final case. So basically, if this is the case, I want to rotate it from theta I to theta f. I want to make it from this position to this position. Then the torque or basically the work done will be the work done will be equals to what? Guys, work done will be equals to what? dw external, which is mv sine theta d theta, and integrated from where to where? From theta I to theta f. Yes or no? Yes or no? What is the integration of sine theta? Hello? People, hello. What is the integration of sine theta? It is minus cos.
Minus cos theta.
write it like this. Minus would be over here. And I'll put the limits cos theta f minus cos theta I. And this will be minus of, or you can multiply this minus inside. The work done will be mb cos of theta I minus cos. This is the work done. But sir, we were doing the derivation for potential energy. This is not potential energy. Please remember, the potential energy is defined as the work done by external agent. Rotate the loop or coil to an angle theta initially the coil was aligned in the direction. So initially when the coil was aligned in the direction of magnetic field, that implies initial angle will be theta 90 degree. Because do you remember, if initially the coil is like this, suppose if this is the case and this is the magnetic field, can you see the area vector is basically perpendicular to the magnetic field, right? Yes or no? In this case it is. So here the area vector is making 90 degree. So basically here you define the potential energy as 0. This is chosen as the reference. So from here, if I am just moving it by an angle theta, then whatever work I am doing is basically defined as potential energy. Please remember this is one formula, and if theta I is equals to 90, then W will be equals to what? The potential energy, and this will be equals to time equal this and theta is equal to W, and this is nothing but your potential. Please write it down. Then is this clear, guys? Done. Hello, guys. Done. Hello, hello, hello.
Yes, sir.
Okay.
Yes, sir.
So please remember these two formulas are main important ones. The work done in rotating the coil from initial to final angle, and the work done like that. Okay. So I'm giving you a question which is directly based on this. A coil having 20 turns and current 10 ampere has the dimension. Guys, are you able to understand the question? So basically, in both you need to find out initially what how is it placed initially. Initially, the loop is placed like this: A, B, and this is the magnetic field. Are you getting my point? Initially, this is like this. The loop is along the magnetic field.
So, what does the second figure mean?
This one.
No, the next one.
This one is for the first and second part. The first and second part, when the loop is initially placed along the direction of magnetic field, then
Okay.
this first and second part, this is the figure. You need to find the torque as well as the potential energy in this case. And for the third, it is rotated from here to here. So you need to find out the work done in this case.
Okay.
Done, guys. Guys, done.
Yes, sir. Done.
What is the answer?
So is torque 0 for the first one?
Yes, torque is not zero for the version. Torque is maximum in this case. The torque is maximum in
Okay,
this
yeah,
case.
yeah, 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 yeah. And
So in the
got it.
first case, guys, can you see the area vector is making an angle? Suppose if this is the top view which you are seeing, then AB is the wire which is at the top. So can you see the wire? It is going from A to B. So can you see when it is going from A to B, the area vector will be pointing in this direction? Yes, applying right hand thumb rule, right? So initial angle is 90 degree. So basically, what is the torque acting in the first case? The torque will be first case. It will be B into I into N into A into sine of degree, which is so this will be just B कितना 2.5 into I कितना 10
10,
amperes. N is 25 turns, right? 20 turns, sorry.
20 turns,
And area is
200 centimeter square
200
by
centimeters square, which will convert into meter square. It will become something like this. And when you calculate this, it will be your answer. Yes.
yeah,
उसके बाद second part, what is the potential energy? Minus of E dot, oh sorry, not P dot E, it is the M dot D, right? So minus of, easy question hai guys, I think you should be able to do it. Is this clear? And please remember here cos 90, actually you will write cos 90, then everything will become 0.
0.
So the potential energy over here in the second case is basically what? Now the third case is basically to find out the work done is rotating, right? So
Yes,
basically that is equals to mb cos theta I minus mb cos theta f. Yes or no? Was this the case?
yes, sir.
Can you see the main application is basically to find out the direction of area? So area vector is like this. This angle is 90 degree. Can you see what is the initial angle with magnetic field?
150,
150. And what is the final angle? What is the final angle?
90.
Hey, 30.
Wait.
Magnetic field के साथ.
Mm-hmm.
Guys, are you understanding the question? See, the only this was it.
So could you explain the last part once again?
Last part, I told you, no, area vector. How to find the direction of area vector? Can you see? The thumb should point in the direction of what? The right hand thumb rule. You use right hand thumb rule to give the direction of area vector, right? Yes or no? So when you move your fingers from A to B, suppose there is a whole loop. When you move your fingers from A to B, so can you see the area vector points towards the that direction, which is mentioned over there. Yes. A and B
Yes.
are you are seeing from the top.
So the loop is placed vertically in the magnetic field.
Vertically. This is a loop A, B, and C is below, and D is also below. You are not able to see C and D. Yes or no? This is just the top view.
Sir,
Okay. What is the final answer?
so why don't we take theta, like cos theta f as 90?
Why didn't we take cos theta f as 90?
Yeah.
Because beta always we take theta is the angle with the magnetic field. Here this was theta I from here to here, angle with magnetic field, and here this was the angle with magnetic field. Yes or no?
Okay, sir.
So that is why we took
Yes.
this as a theta f and this as a theta.
Okay,
So
sir.
this will be now I think you people will be able to calculate it. Huh? Let me give another question. Let me give you another question. We can show the large horizontal coil of radius capital R. Okay. Guys, can you see a bigger coil? It's a very big coil. This very big coil is of radius I, current capital I and radius capital R. The current in it is going in what direction? As seen from top, anti-clockwise, right? Yes or no?
Yes, sir.
Now, if I say this is basically the axis of the bigger coil, can you see the axis of the bigger coil? There is a small coil this is like this. So guys, can you see over here? There is a loop. Can you see there is a very small loop inside? This small loop is of radius small r. It carries a current. Current is small I, and the number of loops in the small is basically n. So basically, can you see over here, guys? From here to here, this is n. The current inside this thing is going like this. Achha, I'll make something simplified for you. Uh, the area vector for, can you see both the centers is coinciding? The area vector for the bigger loop is like this, and the area vector for the smaller loop is like this. This is I'm giving you in the question. So guys, are you able to see the question? Now everyone is able to see the question, right? Hello? Is everyone
Yes,
able
sir.
to see the question? I'll write down the
Yes, sir.
question. This is the things which are given to you. So bigger loop, radius capital R, current I, and there is a smaller loop carrying a current small I, and having a number of turns n turns, is placed. Can you see the center is same? But can you see the axis of this smaller loop is basically making an angle of theta with the loop, not with the this thing. With the loop, it is making like this. So now my question is, here R is much greater than R. Find the torque experienced by the bigger loop, like by the smaller loop. In the figure. Try to do it. देखता हूँ क्या दिमाग लगाते हो. Let me see what will you think of. Give me 2 minutes, guys. I'm just coming. एक second. My mom is calling. Yes, I have available. ना मम्मी बुला रही है. Hello.
Yes.
So done. How is it, guys? How will you do it? See, basically, they have given this condition. What is the importance of this condition? The importance of this condition is basically you will understand, you will consider this smaller loop to be way smaller as compared to what? Way smaller as compared to what?
The
The
bigger
bigger
loop.
loop. So basically, at every point inside this loop, at every point here on the smaller loop, I'll write this thing. Since capital R is much greater than small r, then we can assume that the magnetic field produced by bigger coil is uniform for the smaller coil. Basically, this was the only thing which you need to understand. Now, I think you will be able to do it. The magnetic field produced by the bigger coil will be equals to what? The magnetic produced by the bigger coil, so I will write bigger coil. This will be equals to what? Mu naught by 4 pi into 2 pi I by capital R. Yes or no, guys? Yes or no? Are hi.
Yeah.
Yes, sir.
Now, what will be the torque on the smaller loop if you have considered this as the bigger loop has a magnetic? Now, see the smaller loop. Na? The smaller loop is like this, the area vector of this smaller loop is like this because the current was going like this. And what is the direction of magnetic field due to the bigger coil? Is the magnetic field like this? Guys, can you see over here? Can you see the direction was anti-clockwise? Yes or no? Are yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
So now what is the final answer? Can you see? So by that approximation, you are just assuming that everywhere, the same magnetic field is applied. The same magnetic field. So can you see? We can assume that this magnetic field is uniform for the smaller field. So now the torque experienced by smaller coil will be equal to V into I into N into A sine of theta, right? But what was theta over
90
here?
plus
This was theta and this was 90. The angle between them was what? Basically 90 plus theta, right?
90 plus theta.
So this will be
Yes,
written
sir.
as 90. Is this clear, everyone? Is this clear, everyone?
Yes, sir.
Yes, sir.
So write this as not. So let me solve it now. Mu naught by 2 into I by R into small I into pi R square into what is sine 90 plus theta?
Cos theta.
Minus cos theta.
No, it's plus cos
Plus
theta.
cos theta. Second quadrant.
Ah, yeah, sorry. Plus cos.
I n pi R square upon 2 R cos theta. That is the torque and that is the answer. Clear? So done, guys.
Yes, sir. Done.
Guys, can you see two plates? Let's say these are the two plates which I have given equal and opposite charge. And when I have given them equal and opposite charge, so basically I have created certain electric field like this. Right? Hello? Guys,
Yes.
see the instrument very carefully.
Yes, sir.
By I have taken two plates which I have given equal and opposite negative charge, because what happens? An electric field is created in space. Inside, inside, let's say I have created a magnetic field inside the plates. I have created a magnetic field like this. Okay. So everyone can see a magnetic field. Shall I draw it with a different color? So inside region, I have created a magnetic field like this. Now basically what am I doing? I have a charged particle Q of charged Q mass I. Charged particle. I am throwing this particle with a velocity how much? V. Guys, are you able to understand what exactly is happening over here? So when I am throwing this charge inside at any one particular point, what is happening? Guys, tell me. what is happening at any point inside. Let's say if I say this is the magnet, this is the direction of velocity, then can you give me what all forces will be acting on this charge, and what will be the direction of those forces?
Magnetic force.
There will be a magnetic force in what direction?
Left.
It will be towards left. So there will be a magnetic force which will be equal to how much? QVB towards left. And will there be only this force? Can you see there is an electric
Electric.
field? So hence there will be
Yeah.
an electric field as well, and that will be acting QV, and this force will be acting in this direction. Yes,
Right.
this will be towards left. So can you see, guys? I created an arrangement in which both electric fields and a magnetic field is acting perpendicular to each other. And then with the help of this, what exactly am I doing? I'm throwing a charge particle. Now, if Fe is greater than Fm, then what will happen? What will happen if Fe is greater than Fm? Then this charge particle will deflect in this direction.
Mm. Yes, sir.
This will be deflection, right? In this direction, this charge particle will get deflected. This was the initial velocity, and the particle will move like this. Why? Because the net force will be acting towards right. Similarly, if the magnetic force is greater than the electric force, then what will happen? The particle will displace like towards
Was
left.
left.
This will be the deflection in this case. But if Fm is equal to Fe, if Fm is equals to Fe, will the particle be deflected?
No.
No deflection. The particle moves. That's it. Yes or no? Yes or no, guys?
Yes, sir.
So basically, what is the velocity selector? It is a device by selecting them on the basis of their velocity. So suppose, guys, if I have a proton hai, electron hai, and I have this helium particle, alpha particle, right? I want to select only alpha particle. Then I will, send the charge particles in such a way that the velocity will become, you know, like this. Take a second. Let me calculate what will be the velocity for this. So Q V into V should be equals to Q E. Can you see? From here, V is equals to. So can you see? Only those particles travel in a straight line. Which follow this equation, yes or no? Which travel, right? So are you getting my point, guys? With the help of this velocity, by setting the values of E and V, you are selecting the particles on the basis of their velocity. So that's why this thing is basically called as a velocity selector. This is a device. है ना? Please write it. And generally you will see this type of questions a lot. Guys, there are some questions which are based on magnetic flux, but magnetic flux is the next chapter. It's not here. So we'll discuss, one more formula for work done in a magnetic field is there, but that is in the, with respect to what, magnetic flux. So
Sir,
we'll
can
do
you
that later.
scroll down?
Huh?
Can you scroll down?
Oh, sure. Hello.
Yeah, that's it.
Sixteen 32. Guys, we'll do one thing. We'll write the Q by 2m result as of now only. Because only one type of question is left to create the magnetic momentum. And one last is left, which is Q by 2m case. So we'll do that today itself, and we'll finish up the chapter. In the next class, we'll start with EMI, electromagnetic induction. Whenever you're done writing, just tell me.
Done, sir.
Done? See, I told you that if you can just find out the magnetic moment of any coil, then it will be easy for you to find out the torque and all, right? Yes or no? Acha, I'm giving you this question. Very important type. This is X, this is Y, and let's say this is Z. Okay. There is a loop. Guys, hello. Hello.
Yes, sir.
Guys, see, the
Yes,
type
sir.
is based on this. Till the time the shape is very easy, like the shape is either circular coil or rectangular coil, where every figure was in the same direction. Then you were able to calculate the area very easily, right? Yes or no? Now I'm giving you a loop like this. Can you see a three-dimensional loop? Guys, is everyone able to see a three-dimensional loop?
Yeah, sir.
Yes, sir.
Part A, B is in YZ plane. Part BC is in XZ plane, and CDA part is basically in XY plane. Everyone able to get what exactly I'm trying to draw, right?
Yes, sir.
Part CA, XY. Now the question is, the current in it is going like this. A single loop is there. The number of turns is basically one. This is just a single loop. Now the question is, find the magnetic moment. Acha, by the way, this thing is R. This is a semicircle. So now I think you are able to tell each and every dimensions, right? This is also R. This is also R. Find the magnetic moment of the loop dimension. Yes. Will how will you apply the logic over here, guys? How will you be able to find out the magnetic moment of this thing? Yes, guys. Can anyone please apply some logic over here? This is an illogical problem, literally illogical problem. And my question is, can you apply certain logic to it to justify it? Think. You can have a discussion on your own. Guys, who is not present in the lecture? I think Satvik is not present. Satvik is having connection issues. Who else is absent? Hello? Guys, when did our class start? 3:30, right?
Yes, sir.
Yes, sir.
Yes,
तो
sir.
अपना टाइम हो गया क्या आज का?
No, sir, it ended
It's still
5:30.
5.
Yeah, 5:30.
So it is still 5:30, no? अभी 4:38 only हो
Yeah.
रहा है. अभी टाइम है मतलब. चलो. So is there anyone who would like to try it at least? कुछ तो लॉजिक बताओ यार. How will I solve this problem now? अच्छा हिंट दो हिंट.
Yes, sir. Please.
This is your hint.
Okay, sir, can you show the diagram again?
This is the hint. हाँ okay. Guys ये क्वेश्चन याद है सबको? Everyone remember this, no?
Yeah.
The hint is basically this part, है ना? And I told you in this both the cases. Sorry, I left in between. I was no problem, Ishita.
Yeah.
So see this part, guys. Can you see over here? Here, this case and this case will have the same answer. You know why? You know why? Because that wire, can you see? This wire, they were placed so close to each other that the magnetic field produced due to both of them cancelled out each other's effect, right? So the magnetic field due to these two wires will be cancelling out. Hence, the remaining part and this part will give you the same thing, right? This was the logic. This was the hint. Now the same hint can be applied in this. Can you see over here, guys? What I can do is I can make this loop I can make this loop as basically थोड़ा सा दूर बनाता है so that it will be clear for you people. So basically, guys, are you able to understand what exactly am I doing? The current
Yes, sir.
in this part was basically this. So let it be like this only. You will not be,
Mm.
hampering this thing. The current in this part was exactly like this. The current in this part was exactly like this. So can you see, guys? I broke this single loop into three different loops in three different planes. Yes or no? Can you see if the current is going in this direction? So will the current be assumed to be going in this direction? Will the current
Yeah.
be assumed to go in this direction? And will the
Yes, sir.
current be assumed to go in this direction? Is this clear, guys? And now can you see it very clearly? This current and this current cancels out each other's effect. This current cancels out each other effect. And this current cancels out each other's effect. Just like the hint which I gave. So basically what will be the remaining portion? Only the outer one. Yes or no? Is this clear, guys?
Yes, sir.
So basically, what is this hint in this case? The hint is you can consider this single loop as what? These two are one and the same. Please draw it very carefully. सबको लॉजिक समझ में आया guys? What logic did I apply? Hello?
Yes, sir.
Yes, sir.
Now the question is very easy now. I think so. Let's name the loop as 1, 2, and 3. Or let's not name it 1, 2, and 3. The magnetic field due to, the area vector due to a small loop. Area vector will be due to square root. Will it be having a magnitude of r square and the direction should be, and you see the current is going clockwise. Oh, sorry, anti-clockwise. So will it be pointing towards plus k? Apply right hand thumb rule. Huh? Area vector of quarter circle are you getting my point, guys? This is the area vector. Hence, the magnetic moment will be equal to I into n into a vector, and a vector will be the sum of this vector. Can you see? So it will be I into n is 1, a is r square k cap. Or in spite of writing like this, I can write it like pi r square by 4 I cap plus r square by 2 j cap plus r square. I can take r square also as common. Pi by 4 I cap plus r square by 1 by 2 j cap. This is the magnetic moment vector. The question can be extended. Suppose in the second part of the question, if I give if this that if that loop it is placed in the magnetic field, four I cap plus 3 j cap, है then what is the torque? So I think everyone is able to do this thing. The torque is basically equals to m cross B? Yes or no? So this will be I into R square. And do you remember cross product? Everyone remembers? I cap, 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 5/4, 1/2. I think everyone is able to do this now. Yes or no? Is there anyone who is not able to open up a determinant? Grade 11th, we have learned this thing. Bio people, are you able to open a determinant?
Yes, sir.
You remember you hide the column and the row and then cross multiply, subtract,
Mm.
right?
Yes, sir.
Alternate plus minus.
Yeah.
Yes, sir.
Yes, sir.
So basically, this was the last part, last type of question which was based on, these loops which are not in the same plane. And you see, these loops are not in the same plane. So always remember, for these type of wires, we will not deal with normally. We have to have, connected them like this. अच्छा guys, by the way, एक और चीज ना, most probably my drive, the Google Drive which I keep on sending you the link, it is getting filled now. है ना? So what I'll be doing, I'll be uploading it to the, I'm thinking of creating a YouTube channel on which I'll upload this video. So you people can, I'll send you the link after every class. Or either I can do this or I can make a new ID. दोनों में से एक कोई सा भी ऑप्शन will be suitable this season. ठीक है? Is this clear, guys? Any doubt in this question?
No, sir.
चलिए, last heading. Let's write. This is advanced portion. Please remember. Not for neat people, but still we are doing those. For any uniformly charged body or symmetric charge distribution, the ratio of the magnetic moment and angular momentum comes out to be equal to, always remember, for any symmetric body or for any symmetrical charge distribution, m, the ratio of magnetic moment to angular momentum comes to be q by 2. This is generally mu, which you might have seen in HC Verma and all. This is the concept, guys. Q is the total charge on the object and m is the mass. Small m. This is small m, this is capital M, guys. And a difference. Capital M is magnetic moment, small m is mass of the object. Here, Is this clear, guys?
Yes, sir.
Yes, sir.
This is the concept. Let's see the applications of this concept. Okay, we'll try to have it. Please write it and just give me 2 minutes. Let me. Just guess that, guys. Everyone done?
Yes, sir.
Now let's try to have basically where is this thing used? Please remember this concept will be used in modern physics. When we'll be discussing Bohr's atomic model and all, then this concept will come in very handy. So the question is, suppose first point chart. Suppose, guys, there is a point charge plus q, mass is m, and it is rotating in circular motion with the angular velocity omega and radius is r. Okay. Hello, guys. Yes or no?
Yes, sir.
Yes,
Please
sir.
remember a rotating charge. Whenever there is a rotating charge, a rotating charge can be assumed as a current carrying loop. Can you see, guys, whenever a charge will be rotating about a fixed point or revolving around, rotating a revolving charge. Charge revolving around a fixed point can be assumed as a current carrying wire with equivalent current. I equivalent is equals to. Can you see, guys, over here? What is the charge? Do you remember current is nothing but the rate of flow of charge? So can I say I is basically Q by T? Yes or no?
Yes, sir.
Where T is
Yes, sir.
basically the time period of this thing, and we know the time period is given by what? Omega. Omega is equals to 2 pi by T. So hence from here T will be equals to 2 pi by omega. Yes or no? So I can write Q as 2 pi by omega. This is the equivalent current which can be written as Q omega upon. Yes. Yes or no, guys? Will this be the equivalent current? This is a very important concept, by the way, na? Equivalent current. So don't forget this. So I equivalent is basically Q omega upon 2 pi. Now, can you calculate the magnetic moment? The magnetic moment of this will be equals to what? I multiplied by N multiplied by A, right? So can you see number of turns is not there? The number of turns is there. Kya? Here there is only one single charge. The current carrying loop we are talking. A single turn loop, single turn. Okay. So the current will be equals to Q omega upon 2 pi. N will be considered as 1 and area will be considered as pi r square. Pi से pi कट जाएगा half. Can you see 1 by 2 Q omega r square? Yes or no?
Yes, sir.
Now what is the angular momentum? What is the angular momentum? Angular momentum will be mass into radius r into omega square mr. No, oh, एक second. For those who forgot angular momentum formula like me, I am writing the formula for angular momentum again. है ना? So angular momentum is basically momentum multiplied by r. So that is basically m into v into r. V can be written as r omega. So it will be m r square omega. Okay. Hello people. Is this clear? So if
Yes,
momentum
sir.
velocity is given, radius given, you use this. If velocity, if radius is given, angular velocity is given, then you use this. This is your angular momentum. So here in this case, angular momentum is mr square. This is your first equation. This is your second equation. Can you divide both of them? M by L will be equal to Q omega r square divided by 2. Can you see over here Q omega r square divided by 2, and this will be m r omega square.
M R square
R
omega, right?
square
Sorry,
omega.
sorry. Sorry, my bad, my bad. मैं बोल रहा था कि there is one omega which is getting left. So m r square omega. ओमेगा से ओमेगा कट मारेगा, r square से r square कट जाएगा, and can you see over here m by l is basically Q upon 2. So this is one case. I'll give you another case, and if you know in the case of small element we'll get, and if it comes to be the same again, then what to do? The same thing. Clear? Is this clear, guys? Point charge.
Yes, sir.
Acha, for a ring, will it be the same?
Yes, I think.
For a ring, what will you do, guys? Yes, guys, who will tell me what will you do for a ring charge? If suppose there is this ring which is having certain charge, how much? Q. The mass of the ring is m. The radius of the ring is r. And I want what is the Q by ratio of this thing again. But first of all, what we'll do? I equivalent. Can you see? If I choose a small charge, can you see when I choose a small charge over here for dq? Is this dq revolving in the same time period as the ring? Yes or no? So will this be the di equivalent will be equals to 2 pi by omega, which will be dq into omega upon 2 pi. So when I find out the I equivalent, will it come again the same? Can you see omega 2 pi, everything is constant, so dq will become omega naught. So can you see, guys, in this case and in the previous case, where is it? Can you see the ring case and the point charge case is exactly coming to be the same, right? Yes or no?
Yes, sir.
So basically the same thing will come, and again m by L will be equals to what? Q by 2. Clear? So that's why I'm not doing the whole derivation. I'm just keeping it like this. Is it fine? Third, let's do for rod rotating about one of its.
Sir, can you solve for sphere also?
Yes, I guess. Yes, you can do for sphere. But उसके लिए small element सोचना पड़ेगा. Small element will be like this. Sphere is like this. It is rotating like this. So the current will be in various areas. Right? The current will be different. थोड़ा सा कभी if I go with integration, it will become difficult. But with the help of m by L ratio, you can calculate the magnetic moment of that. मतलब you will use the converse of the concept for calculating for that of a sphere. Suppose guys, I have a rod. Everybody is able to see a rod. Yes or no? This rod is rotating about one of its end with an angular velocity omega. This rod is charged with a charge q and length is L. Yes. Can anyone tell me how will you do this? The mass of the rod is capital M. So basically here in this case, rod uniformly charged, or in spite of writing uniformly charged, you can say there is a uniform rod with a charge plus q divided uniformly, mass M, length capital L, rotating with an angular speed. What is it? Rotating with an angular speed omega. Yes or no? Yes or no, guys? Now again
Yes,
you
sir.
need to find out the same thing as the previous case. So what will you do? We'll choose a small element. Let us say at a distance x there is a small element of width dx. Yes or no? This element has a mass dm and a charge dq. Yes or no, guys? Are yes or no, guys?
Yes, sir.
Although I don't require that mass and all, I just require the charge because I want to find out the current, right? So let's say this small element has a charge d. Now, what will be the equivalent current? Can you see this, guys? This charge will be rotating in certain circle, right? Will this charge be rotating in this circle? Will this charge be rotating in this circle, guys? And what will be the speed of this charge? Although we don't require the speed, it will be not required. So di it will be equals to dq divided by omega. Yes or no?
Yes.
So will it be equals to dq? Okay, sorry, my bad. Sorry. Now, when we choose the small element, can you see over here dq will be equals to q divided by L multiplied by dx? Yes or no? Can I write this over here?
Yes. Yes, sir.
Q by 2 pi L into omega into dx. Will this be your current? If this is your current, then magnetic moment of this small current carrying loop, what will be the small magnetic moment? Guys, what will be the small magnetic moment? Small magnetic moment will be current multiplied by area. Yes or no?
Yes, sir.
What will be the area of this loop?
Pi x square.
Pi into x square. So I can write this thing as q omega by 2 pi L dx into pi x square. Is this the clear? Is this clear, guys? Yes or no? And can you see, once you do this, then you can calculate the total magnetic moment, which is basically T. And can you see q omega 2 pi L, this one more pi will come out of the integration, q omega 2 pi L and this pi. Inside it will be x square dx. This pi and this pi will get cancelled out. And can you tell me where will be the limit? What will be the limits? Can you see from 0 to
L.
L, the length, right? From 0 to L. So the magnetic moment will be equals to q omega by 2L. X square is L x cube by 3, and when you put the limits, it will be L cube by 3 minus 0. Yes or no? So can you see, guys, the magnetic moment is coming 1 by 6 q omega by pi L cube. Yes or no? Are yes or no, guys?
Yes, sir.
Yes, sir.
So there was another L, right?
Yeah, the pi got cancelled, no?
The 2 pi L and
Yeah, pi got cancelled.
This pi got cancelled and there was this L. So basically, this will become will it become this? Yes or no?
yes, sir.
Pi and pi got cancelled. L was there. One L and one L will get cancelled. So magnetic moment is coming this. Now, what is the angular momentum? You remember angular momentum is equals to I omega. And what is the moment of inertia of this rod which is rotating about one of its ends?
ml square by 12.
About one of its end. When it rotates about the
ml
center,
by
then it is
2.
ml square by 12.
Okay.
Otherwise, it is ml
3
square
up
by
to
3. Division 11th grade rotational motion. Okay.
yes, sir.
And can you see over here when you take the ratio again? It is again. Are you getting my point, guys? So can you see, for any symmetric charge distribution which is rotating with a constant angular velocity, you know, this ratio of magnetic moment to the angular momentum is always q by 2. Yes or no? Is this clear? Shall I do one more question? Is it fine? What is the time now? We can do one more.
511.
We can do one more application, then I'll give you a question. 4. The class is still 5:30, right? Hello?
Yes, sir. It's still 5:30.
Yes,
Yes,
sir.
sir.
Suppose now if I have a disk, now you people will be doing, I won't be doing it, right? There is a disk, guys, and this disk has the charge plus q distributed uniformly all over it. The charge is plus q, the mass is m, the radius is r, and this disk is rotating about its center with omega. So now you need to tell me what will be the, again, prove that m by l is basically q by 2. How will you do it, guys? What will be the small element and all? What is the small element for a disk? Yes, guys. Can anyone tell me what is the small element for a disk?
Like a ring.
Ring.
Maybe a ring. So let's draw a ring. Yes. Is everybody able to see that small element?
Yes, sir.
So now, here in this case, there is a small element which is basically what? A ring charge. Charge kitna hona? Ring with charge how much? The charge should be
BQ.
dq, and radius should be, what shall be the radius? From the center, let us assume a small element at a distance x. So can you see, from the center we are assuming the radius as x, and what shall be the width of this thing? This thing shall be dx. Yes or no? The radius x and the width is dx. Is this clear, guys? The small element. Everyone, what is the charge on this? The charge on this is basically dq. Now, can you see over here, guys? Whenever this disk is getting a uniform charge all over the place, hello, guys. If this is a disk which is having a uniform charge which is distributed all over its area, the uniform charge distributed all over its area
Mm.
multiplied by what is the area of the disk? What is the area of this
Pi
disk?
x
Pi
square.
x square.
2 pi x is basically the length multiplied by
Okay, dx.
pi x square is not the area. We don't want the area of the whole ring.
Yes.
We don't want this area, guys. Hello.
Ah,
I
okay.
heard
Yes, sir.
someone saying pi x square. Pi x square is
Mm.
basically the area of the disk which is enclosed. I don't want the disk. I just want this
Yeah.
area.
Okay.
है ना? I just want the
Yes, sir.
area which is there on the ring. So that's why the length of this thing multiplied by the width. Pi say pi gets cancelled, and this is the d. So now what is the current? The current will be dq divided by 2 pi to omega. So this will be q by r square twice of x dx into omega by 2 pi. 2 and 2 will again get cancelled over here. So the di will be basically this much. Now the small magnetic moment. Or in spite of writing small magnetic moment, we can directly write magnetic moment will be integration of dm vector, which will be integration of di multiplied by what is the area. Now you will write the area of this thing. Hello? Hello?
Yes, sir.
Now you'll write the area of this loop. Okay?
Okay.
So now you'll write pi x square over here. Here. So di was equals to how much? Q x dx omega by pi r square multiplied by pi x square. Now you have written the area as pi x square. Is this clear, guys? Guys, is this clear? Any doubt? And then we are integrating it. Q omega pi gets cancelled. R square comes out. Q omega r square comes out. X square becomes x cube. So this will be x cube dx, and the limits will be from 0 to r. So when you solve this thing, this you will get q omega by r square into r to the power 4 by 4 minus 0, and 1 will cancel with this, to 1 by 4 q omega. So this is the magnetic momentum. Now what is the angular momentum? Angular momentum is again I omega. And what is the angular momentum? What is the momentum inertia of a disk about an axis passing through its center perpendicular to its plane? ये गलत बोला तो मार खा जाओगे ना. So please speak only when you are confident. What is the moment of inertia of a disk which is perpendicular, no, about an axis which is perpendicular to the plane of the disk and passing through the center? Disk. Yes, who will say? कौन बलि का बकरा बनना चाह रहा है? Yes, Vaishnavi, what is it? What is it? Hello? No one replying now. Vaishnavi, what is it? Shrishma, what is it?
So is it mr square by 2?
Mr square by 2 half mr square. That is the moment of inertia of a ring, of a disk about its center. Suppose if this is a disk, then the moment of inertia about this axis, if it is rotating with omega, whatever it is, the moment of inertia is half mr square. If it was a ring, it was mr square. If it was a disk, half mr square. So, omega. So can you see again, guys? M by L is basically 1 by 4 q omega r square divided by half mr square omega. So r square omega omega. So can you see, guys? अब मैं नहीं prove करूँगा. I'm not proving it now. After this, I am not proving. ठीक है? Is this clear? Did you understand कि for any symmetric case, if you have the object and the charge is uniformly distributed about it, then always remember the ratio of magnetic moment to the ratio of this thing will always be a constant q by. Is this clear? Sir, where will we use this result? You will use this result in the question like this. A solid sphere, charge q, mass m, radius r. Find the magnetic moment of this rotating sphere. Yes, guys. Will you be able to find out the magnetic moment of this rotating sphere? Guys, can you see again the charge is symmetric, right? It's uniformly distributed all over the sphere. Then what will you do? You will always do what?
Choose a small element.
And not necessary, bhai. What do you need to calculate?
The
magnetic
formula.
moment? Now you know this is a symmetric case, and automatically this will be equals to q by 2m.
Mm-hmm. Okay.
So m will be equals to q by 2m multiplied by L. And what is the angular momentum of a sphere? Tell me. What is the moment of inertia of a solid sphere? Yes, who will speak now? Ishita? What is the moment of inertia of a solid sphere? अरे बोलो, गलत भी बोलोगे बोलो, मैं खाऊंगा नहीं किसी को. आई एम नॉट दैट डेंजरस.
Was it 3 by 5 mr square?
Is it 3 by 5?
Mr square.
4 by 5.
Nah,
2 by 5.
2 by 5 mr square. Guys, please remember, है ना, थोड़ा rotational chapter we have to keep it and always in mind, है ना. The q by 2m, 2 by 5 mr square, 2m, 2m cancel, and the final answer is 1 by 5 q omega. And that is the magnetic moment of this sphere. Acha, what if this sphere was a solid sphere? Anji, what if this sphere was a solid sphere? Then what will be the moment of inertia over here? What was the moment of inertia of a solid sphere? Oh, sorry, hollow sphere, my bad. Even I don't remember.
mr square by 2.
No.
Be the same as a disk here.
Yeah.
Beta, that was a cone. Hollow sphere, it is something. Alright, don't give me like this, yeah. Seven by 5. नहीं, it was not 7 by 5. भाई क्या था? Was it 3 by 4? Was it 4 by 3? कुछ तो ऐसा था. Let me see an image. Solid के लिए it was 2 by 5 mr square. Hollow के लिए कितना था? जहाँ तक I remember it was 2 by 3. हाँ, 2 by 3 guys. Hello. For hollow sphere, I was basically 2 by 3 mr square. Correct.
So, what will be the element in case of a sphere?
A disk with varying radius.
So, we don't take small element here.
We can take it, no problem. If you want, you can take it, no problem, but it will become a little bit typical. है ना? थोड़ा सा for those who want to do the derivation. Can you see a disk? Can you see a disk over here? This is a disk. ऐसा बनता है. At an angle theta, small element d theta, because of which this becomes r d theta, and this radius is small r, this is capital R, तो एक triangle बनता है small r capital R, and it is by small r cross. So anyways, ऐसा guys, these were the basically tools to carry out this integration. Now then, after which you relate r को भी you have to write in terms of capital R cos theta, and then integrate from minus pi by 2 to plus pi by 2. Then you will get your answer. So the solid sphere part is a little bit, the integration is a little bit difficult. Generally मैं class में बताता नहीं हूँ. You want me to prove it? Huh?
No, sir, I'll try at home.
एक बार ट्राई कर, नहीं आया तो फिर I'll send you the proof. Okay.
Okay.
So guys, this is it, and with this thing we are done with your MEC chapter. Even the Q by 2M cases we finished. So finally we are done with MEC. In the next class I'll start with electromagnetic induction. Is this clear?
Yes, sir. Okay.
Okay guys, we'll see you again.
Sir, will you be keeping a test for this chapter? Like in this,
I think
mean,
I'll
like
be keeping it later on, and not in the month of August.
Okay.
We'll keep it in the month of September.
Okay.
By that time, you will have your practice as well, because the material which we have now it's in process. वहाँ से they have started this thing. Delhi people, we contacted them. They said कि yes, we will be dispatching it very soon. Once the वो मतलब hard copy नहीं दे रहे, वो बोले कि soft copy पे we will work on. So very soon you will be getting your modules along. Okay. Okay guys.
Okay.
So you will be having a practice as well. Chaliye. Thank you very much. We'll see you next class.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.
Uh,
Thank you, sir.
Thank you. Thank you very much.